This video is a summary of all the content in the fourth organic chemistry topic in AQA A-level Chemistry for you to use in preparing for an end of topic test or maybe your A-level Chemistry paper 2. In the video we cover naming alkenes, EZ or geometric isomerism including CIP priority rules, addition reactions with halogens, halogenoalkanes and sulfuric acid, and also polymerisation. You know from your GCSE study that alkenes are examples of unsaturated hydrocarbons, molecules that are made from hydrogen and carbon only. You learnt that their functional group was a double bond, although unlike at GCSE where we only met compounds with one double bond, at A-level we are going to meet dienes and trienes. You also learnt that because the functional group is the carbon-carbon double bond, there's no alkene that has a single carbon atom in it. And finally, you learnt that they had the general formula CnH2n. You also used orange bromine water as a test for double or unsaturated bonds, and you saw that if you mixed the bromine water with something that doesn't contain any unsaturated bonds, then it would remain orange, whereas if you mixed it with something that was unsaturated like an alkene, then it would decolorise. Despite the 90-degree angles in the alkene on the previous slide, which actually comes from one of my GCSE presentations, really alkenes are going to look a little bit more like this. One thing that is crucial for you to know is that these are planar molecules, so they're just flat to the page. The bond angle is about 120 degrees. During the GCSE, we named the first four alkenes as ethene, propene, butene and pentene, but now in A-level we start referring to the position of the double bond and also encountering dienes and trienes. So rather than just referring to pentene, we can now have positional isomers like pent-1ene and pent-2ene. And it's also possible for us to have molecules that contain more than one double bond. So this third example is pent-1,3-diene. This carbon-carbon double bond is really important for isomerism, and specifically something called EZ isomerism. So E stands for entgegen, and Z stands for zusammen. And these are German words, and they basically mean apart and together. So the important thing here is this carbon-carbon double bond, because that carbon-carbon double bond is unable to rotate. This happens when the p orbitals of the two carbon atoms overlap, but we'll talk more about this later. In order to determine whether a molecule is an E isomer or a Z isomer, we're going to use something called CIP priority rules. So the first thing that we need to do is to identify the stereocenter, which is just where that double bond is. We're going to look at the four atoms that are attached to the two carbons on either side of that double bond, and we're going to assign them a priority based on their atomic number. And then we're going to look and see, are the highest priority groups on the same side of the double bond, or are they on opposite sides? So here's an example of a molecule where we might be asked to identify whether it's an E or a Z isomer. Firstly, I need to find that stereocenter. So here are my two carbons that are double bonded together. And then I want to think about the four atoms that are bonded to one of those carbons. So carbon has an atomic number of 6 and hydrogen has an atomic number of 1. By rotating it around, it's a little bit easier to see that on the left-hand side we've got our high priority group above, but on the right-hand side we've got our high priority group below. So they're not together, so that means this is an E isomer. If all four of the bonds made by that stereocenter are also to carbon atoms, then they all have the same atomic number. So at that stage, we need to start looking at what those carbon atoms are bonded to. Here's a slightly silly example just to make the point. So we start off, we look at the stereocenter here, and we see that the four atoms bonded to it all have an atomic number of 6 because they're all carbon. So okay, we take each of those atoms and we look at the atoms that are bonded to them. So if I total up all of these, I have an atomic number of 9, whereas if I look down the bottom, then I've got atomic numbers that add to 14. So my high priority group on the left-hand side is my bottom one. And then if I do the same on the right-hand side, we start off and we've got 14 for both of these. So that doesn't really help me. So I need to go another layer out. And then I see that if I include the next here, I get 17. And I get 22. So in this instance, my high priority group is also on the bottom. So I've got 2 on the bottom, they're together, they're zusammen, and so it's a Z isomer. Geometrical isomers are really important when we start to think about the products of a particular reaction and asymmetrical addition. Electrophilic addition reactions involve electrophiles, funnily enough, but in order to understand what an electrophile is and why it's interested in the alkene, we need to understand a little bit about the bonding in that alkene. So most of the bonds in an alkene are sigma bonds. These are covalent bonds that are formed when the orbitals of the electrons from each atom overlap end to end. So all of the carbon-hydrogen bonds in the alkene are sigma bonds, and also the first carbon-carbon bond is also a sigma bond. However, the fourth valence electron from each carbon is part of a different kind of bond. These fourth electrons are in the p orbitals with lobes above and below the carbon. But these p orbitals expand outwards and widen until they meet in the middle, so they're overlapping side to side, not end to end. And this creates one region of space where both electrons from the two atoms may be found. And this is what we call a pi bond. It's a region of high electron density, and it makes alkenes very attractive to electrophiles. The suffix phile literally means liking or loving, so this is chemicals that love electrons. One example of an electrophilic addition reaction that you need to know about is one that's already very familiar from GCSE chemistry, the addition of halogens, such as in the bromine water test. In this, the halogen is added across the double bond to create a dihaloalkane, in this case 1,2-dibromopropane. The mechanism for each type of electrophilic addition reaction is loosely similar regardless of what the electrophile is. Firstly, we have a positively charged electrophile which is attracted to the carbon-carbon double bond. That electrophile is going to accept a pair of electrons from the double bond. This forms something called a carbocation. So cation is obviously a positive ion, and then the carbo bit is telling us that this is carbon-based. And then what we're left with is a negatively charged ion, and that negatively charged ion is going to bond with the carbocation. So let's look at the mechanism for electrophilic addition, this time with a halogen. Our first step is the formation of a carbocation from our initial alkene. Here we've got a bromine molecule, although it could be a different halogen too. I'm just picking bromine because we were talking about bromine water. Whichever halogen it is, that molecule at any moment is going to have an instantaneous dipole. So one end is slightly negative and the other end is slightly positive. And we indicate this using our lowercase delta. So the slightly positive end is functioning as our electrophile. And that is going to be attracted to the double bond because this is the region of high electron density. Now, meanwhile, the electrons in the single bond in between the two bromine atoms, they're being repelled by the electrons in the double bond. So the polarity is actually being increased. And the positive end is getting more positive and the negative end is getting more negative. And this eventually leads to heterolytic bond breaking. So heterolytic means that when it splits, the two sides don't end up being exactly the same. So we're going to have the slightly negative end of the bromine molecule taking both of the electrons and the slightly positive end being left with nothing. So this is how we end up with our carbocation. And then that carbocation is going to react with the anion that's been left over. So when that bromine molecule split apart, the slightly positive bromine atom ended up joining together with the alkene to make the carbocation, and then the other atom formed a bromide ion, a negatively charged ion, and that is now going to attack that carbocation. And this is going to make our product. So we now have a dibromoalkane. The same process can also occur with a hydrogen halide, such as hydrogen chloride, hydrogen bromide, or hydrogen iodide. So in this instance, it's important to note that whereas with the previous example, the delta positive, delta negative could end up any which way around, here the hydrogen is less electronegative than the halogen. So the hydrogen will always be the electrophile, not the other way around. So we're going to have a permanent dipole in this hydrogen halide molecule, and it's going to be the hydrogen that is going to be the electrophile every single time. And then our process is basically identical. So the double bond is that region of electron density, and that's attractive to the slightly positive hydrogen, and also it's repelling the electrons in the hydrogen-bromine bond. So eventually this is going to lead to the bond breaking, and we're going to form a bromide ion, and the hydrogen is going to bond with our alkene to make our carbocation. And then that bromide ion can attack that carbocation, and then we're left with a product that has a single halogen atom added to it. The examples so far have been quite straightforward because the double bond has been exactly in the middle of the molecule. But when it's not, then there are multiple possible options for the product made. Depending on the orientation of the molecule, the hydrogen and bromine from a hydrogen-bromide addition reaction could add like this, or like this, making these two products. Now you might think that we would get an even mixture of these, but actually it's almost exclusively 2-bromopentane. And the reason for this is something called the positive inductive effect, which is all to do with carbocation stability. So alkyl groups, so that's methyl groups, ethyl groups, propyl groups, have a tendency to release electrons. And this is known as the positive inductive effect. Now, when they do this, this is going to stabilise the positive charge of a carbocation. So because they've got those additional electrons, it's almost like it's not quite as positive as it should be. I don't know, that's bad chemistry, but it's how I think about it. So basically the rule of thumb is that the more methyl groups or ethyl groups attached to a carbon, the more stable a carbocation will be. So here's one example of a carbocation, and this one has got one methyl group attached to that carbon there. And we show this positive inductive effect by drawing an arrow rather than just a straight line. So that is not very stable because it's only got one methyl group helping to stabilise it. Whereas this example has got 3 different methyl groups, and so it's very stable. And so that means that that carbocation is much more likely to persist than the first example. After the double bond in the pent-1-ene is broken, there are 2 possible options for what the product made could be, and therefore 2 possible options for which of the carbon atoms has the positive charge on. So our option 1 is that our positive charge is on the first carbon, in which case this is being stabilised by a single methyl group. Or we've got option number 2, where the positive charge is on the second carbon, and that's being stabilised by carbon 1 and by carbon 3, so that is a more stable conformation. So what's more likely to happen is that we end up with that initial carbocation with the charge on the second carbon, and therefore the bromine ends up on the second carbon because the initial hydrogen first went on the first carbon. So your general rule of thumb is that during electrophilic addition with hydrogen halides, the hydrogen will end up on the carbon that already has the most hydrogens. So that hydrogen has gone on to carbon number 1, which already had 2 hydrogens, as opposed to carbon number 2, which only had 1. Now, the last electrophilic addition we're going to look at is a little bit more complicated, and this is using acids. So concentrated sulfuric acid can also add across the double bond, and this is an exothermic reaction that takes place readily at room temperature. And it's going to start the same, but it's going to have a twist at the end. So we're going to start off with some sulfuric acid. And one of the hydrogens in that sulfuric acid is going to be our electrophile. So exactly the same process as before, that electrophile is attracted to the double bond. Meanwhile, the electrons in the bond between the hydrogen and the oxygen are repelled away, so we end up with this bond breaking. And so we end up with our carbocation, where that slightly positive hydrogen has accepted 2 electrons from the double bond, and now we've got our carbocation. And then the rest of the anion from the sulfuric acid is going to come along and attack. So we get this far, but we're not now done. But we've now got one additional step. So now we're going to add further water, and that water is going to split apart into a hydrogen
So we're reforming that hydrogen ion that came from the sulfuric acid so that the sulfuric acid can reform. And then also the OH is going to join up to make our product. So actually the overall effect is that we're adding water across the double bond with the sulfuric acid acting as a catalyst. We also see this very typically in industry when we're trying to industrially make alcohols like ethanol, where we need to use an acid catalyst, often phosphoric acid. So again, we can have something like ethene, and then we can have some kind of acid catalyst providing that hydrogen ion. So we then end up with our carbocation, and then water comes along, and the lone pair is going to attack that carbocation, and then what we're left with is going to be our alcohol, in this case ethanol, and we've remade that hydrogen ion. So typically for a catalyst, the catalyst is being reformed, it's not actually used up in the reaction. In GCSE chemistry, you learned that polymers were very long chains made from repeating units called monomers. The monomers are bonded together in the chain by strong covalent bonds, but then there are weak intermolecular forces between the chains. Now, obviously at A level, we can name these as van der Waals forces. And we know that larger molecules have stronger van der Waals forces. And so, since polymers are very large molecules, they have very strong van der Waals forces. These are much stronger than small covalent molecules like the monomers that they're made from. And this helps us to explain why the vast majority of polymers are solids at room temperature. Addition polymers, as contrasted with condensation polymers, are made from molecules with double bonds, so that means alkenes and also substituted alkenes. If we look at a monomer, then we can see this double bond which will break and polymerise, leading to this polymer. We use the repeated unit nomenclature as a shorthand for a much larger molecule. We name polymers according to their monomers, so this is polychloropropene. But remember that despite that name, this polymer doesn't contain any double bonds anymore, so it's actually a halogenoalkane. In order to name a polymer, the first thing you need to do is to break up the chain into identical repeating pieces called the constituent repeating unit. So here I've got my repeating unit, and if I was going to draw this out fully, of course I put brackets and put the n to show that there are thousands and thousands of this repeating unit. Now, if I was going to draw the monomer that it was made from, it would look quite similar, but it wouldn't have those brackets anymore, and of course it would have a double bond in the middle. We put halogens in alphabetical order, so this is going to be 1-bromo 2-chloroethene, and therefore the polymer is going to be poly 1-bromo 2-chloroethene. You're already aware from GCSE chemistry that polymers tend to be solids at room temperature, and we've discussed the fact that that's because the weak intermolecular forces, the van der Waals forces that hold those chains together, are very strong by virtue of the fact that the polymer chains are very long. But another thing that you might not have thought about is the fact that generally these polymers are chemically inert and non-biodegradable. And this is because we haven't got any double bonds anymore. These are saturated molecules, so we don't have those regions of high electron density to attract electrophiles, and also very often these side groups are non-polar and therefore they're also not really interacting with anything else. The specification says that you should appreciate that the knowledge and understanding of how polymers are produced and their properties has developed over time. So there are two main things I would include under this umbrella. The first one is familiar if you took GCSE chemistry as opposed to GCSE combined science. Polyethylene is a really common and useful plastic, and there are two main types: low density polyethylene or LDPE and high density polyethylene or HDPE. They're both obviously made out of the same monomer, ethene, but what's different is the reaction conditions, and these lead to different properties in the polymers that are formed. Low density polyethylene is made under very high pressure and pretty high temperature too, and oxygen is included as a catalyst. When the polymer forms, it makes lots and lots of branches, and those stop the chains from packing too closely together. In contrast to that, high-density polyethylene is made under relatively low pressure, maybe only 10 atmospheres as compared to about 1,000 for the LDPE, and also a slightly lower temperature, probably about 100 degrees C. It also includes a kind of catalyst called a Ziegler-Natta catalyst. Now, the impact of all of those things is that instead of getting this amorphous structure where LDPE is very, very branched, HDPE has a crystalline structure. So all of these threads are sitting very nicely together because it's comparatively unbranched. You're maybe getting one branch for every 200 carbon atoms in the chain. And so this means that the polymer chains can stack together much more closely, and therefore it's much harder and denser. The second polymer we want to think about is polychloroethene, more commonly known as PVC, because its old school name is polyvinyl chloride. And this is a really common plastic with many uses. PVC contains these chlorine atoms in the side chains. And as we know, a chlorine carbon bond is really quite polar. So you're going to have a permanent dipole set up where the carbon atom at the centre of the chain is slightly positive and the chlorine atom, which is more electronegative, is slightly negative. So you get that permanent dipole. And that means that in between individual polymer chains, we're not just going to have the van der Waals forces, we're going to have much stronger permanent dipole interactions. And so this is going to make unmodified PVC very rigid and very hard. It's also very waterproof. So it's a good choice for things like plumbing and construction. So here is our unmodified PVC, all of these polymer chains very, very closely together. And so they have these weak intermolecular forces between the chains. But then if we introduce another molecule, this plasticizer here, then that is separating out those polymer chains slightly. So here's one example of a plasticizer, and sometimes this will be included with questions that ask you to do something like count the number of hydrogens in this molecule or something. So the point of that plasticizer is that it's keeping the chains further apart and weakening the weak intermolecular forces between them. And so what that's going to do is increase the flexibility and reduce the brittleness. And this is going to make the PVC much more appropriate for things like packaging or fabrics for clothing or the insulation around electrical cabling. Basically anything where that PVC needs to be able to bend and flex without it being rigid and shattering.
Thank you very much for watching, and I hope you're now feeling more confident about this fourth topic in AQA Organic Chemistry. If you did find the video useful, then don't forget to like, subscribe, comment and share the channel for more A-level chemistry videos coming soon.